A visitor from another star system just grazed Mars, and, honestly, the world's most powerful space agencies have gone completely silent. On October 3, 2025, an object named 3I Atlas offered humanity its closest look ever at an interstellar comet, with a fleet of orbiters and rovers all ready to capture history. Yet the only proof of this encounter comes from a ghostly signal teased from public data by amateur analysts. Is this a cover-up, or is the truth far more complicated? Let's explore this together. The flyby. You have to understand, this wasn't just another cosmic event, it was a rendezvous that scientists have dreamed about for decades. On October 3, 2025, the interstellar comet 3I Atlas made its closest approach, skimming just under 0.2 astronomical units. That's about 29 million kilometers from the planet Mars. To put that in perspective, that's closer than any planet ever gets to another, outside of a collision. This flyby was a moment of incredible cosmic alignment. For the first time, a visitor from another star system was set to pass directly through a region of space, monitored by a dedicated fleet of advanced scientific instruments. Every major space agency with a presence at Mars, from NASA and the European Space Agency to China's CNSA and the UAE's HOPE mission, had a front-row seat. Mission planners, like Dr. Jim Bell, the principal investigator for Perseverance's Mastcam-Z cameras, scrambled to redirect their assets. This wasn't in the original mission plan, but an opportunity like this is just too valuable to ignore. The calculations were precise, the stakes were enormous, and the entire planetary science community held its breath, waiting for a flood of data from our robotic eyes at Mars. The promise of Mars. So why was this Mars flyby such a monumental deal? Because our assets there could see what Earth couldn't. As 3I Atlas approached, its position in the sky made it impossible to view with ground-based telescopes, since it was lost in the glare of the sun. But our Martian orbiters were in the perfect position. Think about what that means. NASA's Mars Reconnaissance Orbiter carries the HiRISE camera, an instrument so powerful it can spot a coffee table on the Martian surface from 300 kilometers up. In theory, HiRISE could capture images resolving the comet's nucleus or any fragments breaking off with unprecedented detail. Then you have the spectrometers. ESA's Mars Express and the Trace Gas Orbiter are equipped with instruments like Omega and Nomad, designed to detect trace amounts of gases in an atmosphere. Pointed at the comet's coma, they could have sniffed out its chemical composition, telling us if it was made of the same stuff as our comets, or something truly alien. Dr. Amy Mainzer, a leading expert on comets, has emphasized that these objects are pristine leftovers from the formation of other solar systems. Getting a direct chemical reading from 3I Atlas would be like analyzing a core sample from a planet being born light years away. A faint signal emerges. With the world's space agencies silent, the first and only evidence of the flyby came not from an official press release, but from the hard drives of two persistent citizen scientists. Enter Björn Jansson and Kevin Gill, two names legendary in the community for their meticulous processing of raw space images. Working independently, they went directly to NASA's Planetary Data System, the public archive where raw data from missions like Perseverance is posted. Within hours of the data being downlinked, they began their digital excavation. Their process was painstaking. They took dozens of long-exposure images from the Mastcam-Z camera, which were designed to look at the dark Martian sky. By aligning each image based on the background stars, and then digitally stacking them, they could amplify the faint signal of anything that moved through the frame. After methodically subtracting sensor noise and cosmic ray hits, a faint, diffuse patch of light emerged, right where 3I Atlas was predicted to be. It wasn't a spectacular photo, but it was monumental, the first and only direct confirmation that the interstellar visitor had made its historic pass. Their work stands as a testament to the power of open data. The auditable path. Let's break down exactly how that faint detection was proven to be real, because this is where science separates itself from speculation. The process begins with the raw data. On October 3rd, Perseverance's Mastcam-Z instrument took 36 long exposure frames, each lasting 29 seconds. The next day, it took 40 more. The first step for analysts like Johnson and Gill was calibration. They retrieved matching dark frames, images taken with the lens cap on, to map out the sensor's inherent electronic noise, and subtracted it pixel by pixel. Next came flat fielding, a process that removes distortions caused by dust on the camera's optics. The most critical step was registration. Each image's star field was perfectly aligned with a projected star catalog, correcting for the rover's slight movements. Once aligned, they used a technique called sigma clipping to reject outliers like cosmic ray strikes. Finally, the clean frames were stacked. The result was a master image where the random noise was averaged out, leaving behind a faint but statistically significant signal. A diffuse spot of light exceeding the background noise by a factor of 5 sigma, the gold standard for a scientific detection. This entire workflow with all its scripts and calibration files was published online for anyone to replicate. Viral myths and reality checks. In the vacuum of official information, the internet did what it does best. It generated myths. The moment the faint real detection began to circulate, so did much more dramatic but fake images. The most viral was a sharp, razor-thin streak of light in a single frame from Perseverance's navigation camera. It was hailed as a naked-eye view of the Interstellar Comet, but the truth required a dose of orbital mechanics. Dr. Emily Lakdawala, a renowned planetary scientist and author, did what any good scientist does. She checked the numbers. Using JPL's Horizons Ephemeris tool, which can predict the position of any known object in the solar system, she plotted the streak's path and timing. The verdict was undeniable. The streak perfectly matched the speed, orientation, and sky path of Phobos, Mars's inner moon, during a long exposure. The second myth was a bright, fast-moving streak in a different Mastcam Z frame. Again, the math didn't add up. Its angular velocity was at least 10 times faster than 3I Atlas was predicted to be moving. It was likely a meteor in Mars's upper atmosphere, or a simple sensor artifact. These episodes were a critical lesson in scientific literacy. Not every streak in the sky is a visitor from another star. The silent orbiters. So, where is the real data? Why the deafening silence from the orbiters? Mars Reconnaissance Orbiter, with its HiRISE camera, could in theory deliver the sharpest images ever taken of an interstellar object. Its narrow field of view makes every shot a gamble, but a successful one would be revolutionary. The European Space Agency's assets, Mars Express and the Trace Gas Orbiter, offered a different promise. Their spectrometers, Omega and Nomad, aren't just for taking pictures, they're for reading chemical fingerprints. They could have detected unusual isotopic ratios or molecules that would definitively prove 3I Atlas came from a completely different type of star system. Even the UAE's HOPE and China's Tianwen-1 orbiters were poised to contribute wide-angle monitoring and spectral data. The promise was real. Dr. Candace Hansen, a veteran planetary scientist who worked on multiple Mars missions, knows the immense capability of these instruments. The fact that not a single raw frame, not even a low-resolution thumbnail has been released is the central mystery of this event. The data almost certainly exists, locked behind a wall of institutional review and processing backlogs. The knife's edge. The silence from the space agencies probably isn't a conspiracy. It's a reflection of the brutal reality of deep space operations. Pointing a spacecraft at a tiny, fast-moving object millions of kilometers away is, honestly, an exercise in controlled terror. The ephemeris for 3I Atlas, its predicted position, was being updated hourly. But the orbiters can't just react in real time. The commands to turn, point, and shoot have to be programmed and sent hours or even days in advance. It's what engineers call open-loop pointing. You shoot and, well, pray the target crosses your field of view when you scheduled it to. Then there's the Deep Space Network, the communication lifeline to Earth. Every bit of data, from every mission at Mars, competes for limited bandwidth. A historic image from HiRISE might have to wait in a queue on the orbiter's solid-state drive for days behind higher-priority engineering telemetry. A single missed DSN window or a slight drift in the comet's predicted path could mean the difference between a Nobel Prize-winning image and a frame filled with empty black space. This is the knife's edge of interplanetary observation. Blinded by the sun. Even if the data exists, there are two massive roadblocks preventing its release: solar geometry and calibration. As October moves forward, 3I Atlas is heading for superior conjunction on October 21st, which is basically the point where it's almost directly behind the sun from our point of view. And, this isn't some kind of policy, it's just plain physics. The sun's overwhelming radiation makes both communication and observation totally impossible. For about 6 weeks from mid-October through early December, Earth is, well, pretty much blind. That means the comet's most active phase, as it gets closer to the sun, will happen while we're just not able to watch. Meanwhile, back at JPL and other places, the data pipeline is really a gauntlet. A raw image from space is nothing like a photo you'd snap on your phone. It's full of cosmic ray hits and sensor artifacts. The specialized software pipelines, like the ones from Malin Space Science Systems who built Mastcam-Z, are tuned for static Martian landscapes, not for faint moving targets like this comet. Releasing an uncalibrated frame would be irresponsible, honestly, and could spark another wave of viral myths. So the teams have to be meticulous, and that careful work just takes time, all while a government shutdown is making the delays even worse. The world is waiting, not because of a cover-up, but because we want good science. The working hypothesis. Based on the limited data scientists gathered before 3I Atlas vanished into the sun's glare, they do have a working hypothesis, but yeah, it's still full of questions. The current theory is that 3I Atlas is a natural interstellar comet, but with some really weird chemistry. Early spectra suggested it's rich in carbon dioxide ice, but surprisingly poor in dicarbon, which is the molecule that gives most of our solar system's comets their classic green coma. That kind of points to an origin in a star system with a really different chemical makeup or temperature gradient than what we see here. Some of the provisional reports even hinted at a possible excess of metals like nickel in its dust. A finding that, if it's confirmed, would be truly bizarre and honestly pretty tough to explain. Dr. Stephanie Milam, who's an expert in comet chemistry at NASA, would be absolutely chomping at the bit for that orbiter data, since only high-resolution spectra can confirm these tantalizing hints. But without that data, the natural comet scenario is just that, a hypothesis. The real proof is still sitting on a hard drive, just waiting to be processed. What remains and what comes next? With Earth-based telescopes blinded until December, the world is watching those few assets that might, just maybe, catch a glimpse of 3I Atlas. The SOHO spacecraft's LASCO C3 coronagraph is able to monitor the area around the sun, but its limiting magnitude is actually pretty bright, like around 8 or 9, so it's only going to spot the comet if there's a dramatic outburst and it suddenly gets a lot brighter. Another long shot is ESA's JUICE spacecraft, which is currently on its way to Jupiter. It might have a brief window in early November to try some deep field imaging, but honestly, the real hope comes in late November and early December. That's when Earth's orbit will finally give us a clear view again. Large ground-based observatories and a whole network of skilled amateur astronomers are already planning their recovery campaigns. The big lesson from this whole event is pretty clear. Our current observation capabilities have a massive blind spot. Without more deep space telescopes parked in different places, like the proposed NEO Surveyor, the next interstellar visitor could just fly right past us, completely unseen. The story of 3I Atlas is, well, a cliffhanger. We've got a confirmed detection, a mountain of unanswered questions, and the most important data in a generation just locked away, waiting to be processed. This event has really shown both the incredible power of our robotic explorers and the super frustrating limitations of deep space science. Was this just a strange comet, or could it actually be something more? The answer is coming, but for now, we wait. It's a powerful reminder that the universe still holds deep mysteries, right on our cosmic doorstep. Don't forget to like, subscribe, and hit the bell icon for more explorations into the cosmos. Thanks for watching InnoVision Tech.